Okay. The first test will be given on Wednesday the 26th, 2 weeks from this week. And what it will cover is everything that has been covered in, will be covered in Chapter 2, which will be finished this week, and also one section of Chapter 3 that will be covered next Monday. So next Monday is when all the material that will be on the test will be finished. So class time on the 19th. Nothing new. That'll just be a review. And in particular, we can talk about the practice test that I recently posted on the site. So you go to the course website from a main Canvas page. There's a link there. So if you go to the lectures page, same page has a link to all the class videos. On the entry for the test, February 26th, you will see practice test and solution. Okay. So at this point, we won't know how to do all those problems, maybe about half of them after today, but soon we'll see the rest of them. Also, if you look at the PDF for the practice test itself, if you look at the last, there is a formula sheet. So that exact same formula sheet will be given out with the test. So you'll see in advance, here's what you don't have to commit to memory. A certain solution formula and all that. But you still have to be able to apply those. There will be a total of 7 problems. Okay. Well, there's 8 problems, but one of them is a bonus. So 7 problems, 15 total of 105, but I will still grade a test out of 100. So a regular problem, if you get them perfect, you'd have a higher than perfect score. With a bonus thrown in, the maximum possible score is 120. The bonus problem is being kept under wraps because it's bonus. But the idea is, what do you see in a test? There are certain types of problems: solving a separable equation, solving a linear equation, solving an exact equation, with or without an integrating factor, etc. Formulating differential equation for an application problem, that'll be on there. So it's basically one problem of each type, and that is exactly what will be on a real test. So once you see the test, no one can grumble to me that they didn't see this coming. So be sure to look at that soon, and so that at the review I can handle questions on it, and I'll talk about the different types of problems. Yes.
The solutions are going to be posted right before the test on February.
No, I never said that.
You wrote it down on February.
On the calendar. So this is the entry that you look at to see the practice test.
Oh, okay.
It's there now. I actually posted on Friday. So everything, practice test, solution formula sheet is there now. Okay. All right. Okay. Let me clarify that on the board. Okay. For anyone who watched this video, which will be quite a few people since they're not here. Okay. Any questions about this? I'm sure there'll be plenty later. Okay. Now, now after seeing or a different type of equation, bless you. Okay. Now to recap the general framework I'm using to come up with solutions for different types of equations. Solving y prime equals f of ty with possibly initial condition y of t naught equals y naught, and rewriting in this form where mu is some scaling factor, some integrating factor. That'll be particularly important for today's type of equation. It can be a function of either t or y. Okay. And the implicit solution that we're looking for, that can always be used, is some function big F of ty is equal to 0. And I won't repeat all the steps that I've done before, but because we're looking to describe a solution in this manner, this leads to an equation that mu has to satisfy. That minus d mu dy times f minus mu df dy is equal to d mu dt. So this is, so far I'm not talking about any specific type of first order equation, is any first order equation. And to contrast what we're doing today with what was done last time. So last time, if the equation is separable, okay. Pet peeve of mine, if I see any of you write a word with an E here instead of an A, I'm flunking you. Yes, I may be my professor, but in elementary school I was also a spelling bee champion. So, okay. So in the case of separable, that's where f turned out to be a function that could be written this way. And what was done to solve it was we assumed that d mu dt is equal to 0. So mu would be a function of y only. And the choice that was made is 1 over h of y, the y part of f. So that's 45 words or less summary of what was done last time. Now, assume that f has a different form. F of ty is equal to some function of t times y plus some other function of t, I'll call q of t. Now, the minus is really just notational convenience for later. Okay, so I'm putting these side by side because when you are dealing with equation, like for example on a test where it's not given to you, the equation is separable or the equation is linear, it's up to you to tell the difference. That if you have a function f of ty where this part is like y squared, then that's definitely not a linear equation. This is the only way in which y can be involved. It's by itself times some function of t. There's no other involvement of y in the whole time derivative. Okay. So if it fits this form, then we make the opposite assumption, that d mu dy is equal to 0. So we have our scaling factor, integrating factor, is a function of only t. Now, I haven't said yet what function of t, but we're going to in a minute. So now what I can do is I go back up here to this equation and now take advantage of everything that I know. So if I repeat that, uyf minus mu fy is equal to d mu dt. So I just said that d mu dy is 0. So that term is gone. So now what I can also say, I can also specify what fy is. So if f of t and y is equal to minus p of t, y plus q of t, then the derivative of this function with respect to y, anything that depends on t is considered a constant. So it's just going to be minus p of t. So that's going to simplify things considerably also. So now I will take this and substitute it in here. The minuses will cancel. And what's left is mu of t, p of t is equal to mu prime of t. Okay. Now, this kind of equation we've actually seen before in various instances. So I can simply write down what the solution is. This is actually a separable equation. So what we get is mu is e to the integral of p of t dt times the constant. Now, mu is something I'm multiplying the whole ODE by. So any constant factor isn't really going to matter. I can pick whatever I want. So whatever arbitrary constant I might have here multiplying is, I'll just say it's 1. So this is the scaling factor I need to make the equation solvable. All right. And this is referred to as the integrating factor. Okay. So now, we want our implicit solution now, big F of ty. So the function actually describes the solution. So that is just equal to the integral of mu with respect to y. Now in this case, the integral is particularly easy to do because we're integrating with respect to y, but the integrand is not a function of y, it's a function of only t. In other words, we can treat it as if it's a constant. So all we get is mu times y, and then we have to add on the plus c, which really is going to be some unknown function of t. So when you have a function of t and y, you integrate it with respect to y. What you add on is something that does not depend on y, but it can depend on t. So once we know this, we're done, and I can write down a solution formula for you. Okay. Now, how that is done, we have this equation that must be satisfied. Derivative of capital F with respect to t must be equal to minus mu f. So I'll fill this in. So mu y plus c, derivative with respect to t, must be equal to minus mu times f, which is minus py plus q. Now, if I take the derivative on the left side, I have mu prime y plus c prime on the left, and this is equal to mu py minus mu q. But keep in mind, though, what is mu prime? Mu prime is over here. Mu prime is equal to mu times p. So I can fill that in. Mu py plus c prime is equal to mu py minus mu q. What simplifies?
Mu py.
Yeah, we have mu py both sides. Gone, gone. So now, c prime is minus mu q. So c, we take the integral. There's a minus here. Integral with respect to t, because c is a function of t. Let's make that look more like an equal sign. Okay. So now I can specify the solution completely. So the solution is described by this equation, big F of ty, which is mu of ty minus integral of mu q dt is equal to 0. That is an implicit solution. But the nice thing about this linear case is we want to solve for y explicitly. And in this case, it's easy to do. I just have to move this over to the other side and divide by mu of t. So y of t, the explicit solution, is 1 over mu times the integral of mu q. Okay, so I'll box them in a box. So if you're given a linear equation, so you identify what is P, what is Q. This is the first thing you do. Get your integrating factor. That involves integrating P. Once you have that, bam, there's your solution formula. Another integral to work out, unfortunately. Now, very important here. I'm going to put this in brackets, the integral. Not absolutely necessary, but I'm emphasizing this because note that this 1 over mu of t is multiplying the integral. Therefore, when you work out the integral, there's going to be a plus c involved. Don't forget to multiply the plus c by this. So this is multiplying everything that's involved with that integral. So the common mistake is to forget that part. Mu is an exponential of something. An exponential is never 0. It's always strictly positive. So we never have to worry about dividing by 0. Because this is within an integral sign, you cannot cancel these. After you work out the integral, often there is an opportunity for some kind of cancellation. But do the integral first and then see what you can do algebraically. Okay. So, right. So integrating factor, and then this is your solution. Questions about how that was obtained? Okay. Now, so far I've not talked about an initial condition. When there is an initial condition, and you can either use exactly what I wrote over there, when you have a plus C, and you can use the initial condition to find out what C is. Or you can take the initial condition into account from the get-go. Okay. Now, okay. So if we have the original ODE with scale, you can always write it this way. Now this comes from y prime is equal to minus py plus q. So that's for general linear equation. And now you can see why I put the minus here. I'm moving this to the other side. So now I have y prime plus py is q. And then I multiply both sides by the integrating factor. Now, if we keep in mind that mu times p is the same as mu prime of t, because that's the way the integrating factor was defined. Here I have mu y prime, and here I have y mu prime. What differentiation rule in calculus, as you learned in Cal 1, gave you an expression like that? Two terms, each one function is differentiated, the other is not. Yes, that is the result of the product rule for differentiation. So I can condense this into mu of t, whoops, that's a really squiggly y, mu of t y of t prime is equal to ut qt. So this is another way of looking at what the solution is, because now I can integrate. If I suppose I integrate both sides with respect to t, but I'm going to use I've done this in previous cases, a definite integral. With limits t naught, which is the initial time, and capital T, which you think of as the final time, but it's how we're going to express a solution. Okay. And this is where if it comes from y of t naught is equal to y naught is our initial condition. Now, integral cancels out the derivative. It's fundamental theorem of calculus. You just have to plug in the limits. So I have u of capital T, y of capital T, minus mu of t naught, y naught, the initial condition. And then I can't do anything over here just yet. Because q could be anything. We wouldn't know how to do that. Integral. Now, I'm going to let the integrating factor be defined in terms of definite integral also. of P of t dt. I'm still using that, except now I'm going to put limits on it. So I'll fill in the same limits, T naught down below, capital T up above. And the reason why that's convenient is suppose I plug in capital T equal to T naught. I put T naught up here. What happens? What does it become? I'm integrating from T naught to T naught. What is 0? Not the whole thing, but
The one, the total would be 1.
yeah, because if I plug in T naught up here, I have integral from T naught to T naught. Integral from one limit to the same limit, 0. So I have e to the 0. So mu of T naught is e to the 0, which is 1. So now I can ignore that, I just have a 1 there. Okay. So now I can solve, I want to solve for y of capital T, that's my explicit solution. So y of capital T is to 1 over mu of T y naught plus integral T naught to capital T, wait, I need, okay. Integrating factor outside. Integral from T naught to capital T, e q t dt. So this is an explicit solution that takes into account the initial condition. Right. If I were to fill in what the integrating factor is, so this can be plus e to the minus integral T naught to capital T P of T dt plus here we have the integral from T naught to little t. Here I have the integral from T naught to big T, only it's negated. When you have a definite integral and you negate it, what happens to the limits?
You change it.
Yeah, switching the limits is the same as negating the integral. So, okay. So this would be the same as integral e to the minus capital T to T q t dt. Saying the same limits out here. Okay. I have to actually fill in the integram. But in here I have to use a different letter. Because I have little t as a limit of the integral, I have to use a different letter inside. Okay. All right. Sorry, I just have to check something in my notes here. Okay. Now, for whatever problem you're given involving linear equation, this solution formula over here can always use that. It's just there's some, if you give initial condition, there's some extra algebra involved. So, yeah, just giving you options. But I want to show you how the initial condition manifests itself in the solution. Okay. So now, do some examples. Now suppose y prime is equal to that. In other words, I've set q of t equal to 0. So it's still a linear equation, just a simpler one. But what other kind of equation is this besides linear that we've seen? What? Yes. So an equation like this is both kinds. So if we have the same kind of initial condition, then the solution formula that we've seen before, y of t is just going to be this term right here. So it's going to be the integral from t naught to t of ds y naught. Okay, so that's a solution formula that takes into account the initial condition. All right. So whether you treated this as a separable equation and used the approach from last time, or treat it as a linear equation, this is your solution. Now, let's see. Okay, so it's supposed to have y prime plus 1 over t times y equals sine t. And I'm not specifying initial condition in this case. So, very first thing, identify your p and your q. So if you have it written like this, y prime plus something times y. So anything involving y on the left side. Whatever's multiplied, and also sometimes the equation might be given to you of something multiplying a y prime. Divide by it immediately. Make sure, before you use any solution formula I've written down here, these are meant to apply to an equation in a specific form. Get it in that form very first thing. So make sure y prime's by itself. Make sure y is also on the left side. Then this is your p of t. And whatever's on the right side will be a function of only t is your q. All right, so you write that down. Like this is your p, this is your q. Okay, now, as I indicated before, the first step, work out the integrating factor. That's e to the integral of your p, whatever that may be. So that would be e to the what? E to the natural log of t. Which simple, and we're assuming here that t is positive because at t equals 0, but the equation itself is undefined anyway. Simplifies to what? T. Okay, so that is your integrating factor. It's just t. So now you can jump directly to the solution formula. Since there is no initial condition given, I'll just use this one right here. So that would be 1 over t sine t dt. All right. But getting far. What's needed to work out that integral? What technique do you need to use? Integration by parts. And when you have a polynomial times a sine or a cosine, also if it's an exponential, we saw that last time, let the polynomial be the u. So, all right, so I was just make a chart, u, v, or table d, u, v, du, and dv. So u is whatever power of t you have. So du is just dt. Everything else goes into the dv. So that is sine t dt. And then you have to anti-differentiate that to get the v, which is what?
Cosine.
What? Sorry, say again? Negative cosine.
Negative cosine.
Yeah. Okay. All right. So now, integral of t sine t dt is u times, well, I'll write the formula, uv minus integral of v du, in case you've forgotten from Cal 2. So we're going to have minus t cosine t minus the integral of v du. So a minus and minus will make a plus. So it's plus integral of cosine t dt. And the integral of cosine is just sine. Okay, so that is what the integral works out to. So now we can work that back into the solution formula. Whoops, sorry to whoever's watching at home. Okay, so y of t is going to be 1 over t times all that. Don't forget the plus c. Okay, so in the very first term, the t's will cancel. So we have minus cosine t plus 1 over t sine t plus 1 over t times c. So if you were given an initial condition, then you said you put your y naught over here, you substitute your t naught throughout, and that's when you'd have to solve for a value of c. Again, your 1 over your integrating factor out front. Don't forget to distribute through everything, including a plus c. So questions there? Do another. Next, I have y prime plus y is equal to t e to the minus t plus 1. So this equation is also written in the form it needs to be in, where y prime is by itself. And then the y term is also on the left side. So here's your p of t, it's just 1. And this is your q of t. So mu of t is e to the integral of p of t. So what does that turn out to be?
T.
Yeah, so here we fill in 1, so we get e to the t. Okay, so now we go to the solution formula. Y of t is 1 over mu, integral of mu times q. What I would recommend, since your integrating factor most times, now it wasn't last time, but in cases where it is really is exponential of something, even after you simplify, I would recommend writing it this way. Don't take 1 over e to the t, write it as e to the minus t. So just negate the exponent. That'll make things easier later. Here we fill in the integral, e to the t, and then q of t, t e to the minus t plus 1. So before we integrate, you should take that e to the t and just distribute. Leave the e to the minus t outside though. So inside the integral, what does it simplify to? What's that first term simplified to? I'm sorry, I heard something, but...
T.
Yeah, just t, because you have e to the t and e to the minus t. Those will cancel because you have exponents being negatives of one another. You'll cancel, you get e to the 0, which is 1. Now, this kind of thing is going to happen all semester long, where you have big mess of an expression, and you have exponentials with exponents that are negatives of each other, they'll cancel and become 1. So it's important that be at the front of your mind as something to handle quickly, just because of its frequency with which it occurs, in this class anyway. So we get t, and then the second term, yeah, just e to the t. All right, so when you solve this, a t even minus t, you might think, oh, that's going to require integration by parts again. But you're not integrating that. You're integrating that times the integrating factor. So this turned out to be nicer. So what's the integral work out to? Yeah, t squared over 2 plus e to the t is its own integral, plus c, don't forget that. So then you can go ahead and you can also stop here, or you can distribute the e to the minus t through, which would cancel with this and give us a constant term. And then you have 2 terms of an exponential in them. Okay. Although actually, I'm going to go ahead and distribute because, so here e to the minus t, e to the t, that gives us a 1. And then there's e to the minus t, t squared over 2, plus a constant. So because in this form, it's easier to see how the solution behaves as t goes to infinity. So as t goes to infinity, what happens to the solution?
Goes to infinity.
No, actually. You might have thought it goes to infinity because of a t squared over 2, right?
Yeah.
Does it go to 0?
Yeah.
E to the negative?
Not the whole thing. But yes, this part goes to 0 because of the e to the minus t. But 1 remains. So the limit as t goes to infinity of a solution. So is 1. So the t squared over 2, that part's going to infinity. The e to the minus t is going to 0. We're competing against each other. The exponential is always going to win. E to the minus t goes to 0 faster than any power of t goes to infinity. Okay. Okay. Now, this term that goes to 0 as a name is called a transient term. So I mentioned this because it comes up in the homework. You're given various linear equations. When you solve them, one other thing they'll ask you is, what is the transient term of solution? It's any portion of your solution that you've just typed in for the solution box that's going to go to 0 as t goes to infinity. So when you have these decaying exponentials, so these are things to look for. E with a negative exponent, or negative to the powers of t. Like if you have a 1 over t or 1 over t squared multiplying something. So if that something does not grow faster than that, then that part is also going to go to 0. Okay. Now, so you can almost think of the non-transient part, this part right here, the 1. It's almost like a equilibrium solution in a way. So it's not really, because equilibrium solution comes from autonomous equations where the time derivative doesn't depend on t at all, only y. But it kind of is just because if you look at this, as t goes to infinity, this part's going to 0. So even though this is not an autonomous equation, as t goes to infinity, it kind of converges to 1. And if you ignore this term, because it's going to 0 anyway, and treat it as an autonomous equation, you would have an equilibrium solution of y equals 1. Okay. All right. So questions about this example before I do another? Okay. All right, so this is written in a little different form. Ty prime plus y is equal to 6t plus 1. And here, the initial condition specified, y1 is equal to 9. Actually, I just wrote this problem straight off of homework, except the numbers may be different. You're welcome. Now, first thing, get it in the right form. Y prime is not by itself. So you need to divide through by t. So y prime plus 1 over t y is equal to 6 plus 1 over t. All right, so do that first thing. Now it's in the right form to identify your p of t. And this is your q. Now, if you look at p of t, so this is something else that comes up in homework, is undefined at t equals 0. So when you have a point like that, or a point where p of t is undefined, which is the same thing as if you have a coefficient out here that's equal to 0 here, so then you'd be dividing by 0, that is called a singular point. So that's something that's mentioned in the homework, because one of the things they ask is what interval is the solution defined on. Now, when you have your solution worked out, you can look for certain things that cause it to be undefined, like dividing by 0, square root of a negative number, or natural log of a non-positive number, things like that. But this should be taken into account also, that whatever your p of t is, if it's undefined anywhere, then that should be taken into account in determining where the solution is defined. Okay. So when you see a term in the homework, that's what it means. Okay. Now, the p of t we actually dealt with in the previous example. So integrating factor would be e to the integral of p of t. So e to the integral of 1 over t. So that is, and our initial time is positive, y equals 1. T equals 0 is 0 point. So we're dealing with the right half of a number line, t being positive. So factor is just going to be t, like it was 2 examples ago. So now, solution formula. All right, so we filled in our pieces. So mu is t. So then I have t times q, which is 6 plus 1 over t. But at least this is going to simplify. So it's going to be 6t plus 1. So what's the integral of 6t plus 1?
T squared.
3t squared, yeah, because it's 6 times t squared over 2. So 3t squared plus
T.
t. Right, and then do not forget the plus c. So now we have our general solution. That applies with whatever initial condition. But now we have to enforce the initial condition. So we set t equal 1 and y of t equal to 9. So y of 1, which is 9, but that is equal to this with t equal 1. So I have 3 times 1 squared plus 1 plus c. Okay, so what is c?
Five.
Yes, 5. Yeah, because I have 4 plus c. So now I can simplify this and write down a solution. So y of t, solution to our initial value problem, is going to be 3t plus 1 plus 5 over t. Okay. Now, what part of this solution, which of these terms would be called a transient term? In other words, it goes to 0 as t goes to infinity.
The last one.
This one, only that one. All right, so that part goes to 0, but as a whole, the solution is going off to infinity because of the 3t plus 1, so your function of t. All right, so this is your transient term. So a term that is not going to stick around for the long haul. So transient term and singular point are two terms that arise in the homework on this section. Okay. So because t equals 0 is a singular point, and we also see here that this solution will be undefined at t. Also, the initial time, here, t equals 1, so since that's positive, then we can say the interval of definition is from 0 to infinity, open interval, so it's excluding t equals 0, which is already known to be a singular point. So this is the largest interval in which it's possible to define this solution. Whereas if the initial condition had been specifying a negative initial time, which would be kind of strange, but mathematically you can do it, then up to 0 would be the interval definition in that case. So when you're making an interval definition, it has to be an interval that contains the initial time if an initial condition is given. Questions about this one? Yes?
In the general solution, before you go to the initial condition, would it be better to go ahead and knock out that 1 over t and that be just 3t?
Oh, like distribute that?
Yeah, distribute that first and then go into your initial condition?
Most cases, yes. I think I didn't do it. But yeah, there's a good chance that simplifies things for most problems. Other questions? Regarding homework. Okay. Well, I've reached the end of my notes, so if anyone has homework questions they want to ask me individually, I will stick around. And we'll see exact equations on Wednesday.